Welcome to The Explainer, everyone. I'm Dr. Chem. The physical world around us, it's just this astonishingly complex, sometimes totally chaotic mixture of molecules. And to really understand it, to use it safely in medicine or industry or science, we've got to be able to organize it first. So welcome to the invisible architecture of our world. I mean, think about a single drop of human blood, a plant leaf, or even a polluted river. These aren't just things, they're literal oceans of complexity. So how exactly do we find one single hidden molecule floating around in that vast mix? Well, we rely on absolutely one of the most essential and powerful separation techniques in all of analytical chemistry. Okay, let's dive into this. The whole story of organizing these molecules actually starts way back in 1906 with a Russian botanist named Mikhail Tsvet. He was trying to separate plant pigments, like the green chlorophyll you find in leaves. So he poured a plant pigment solution down a column packed with absorptive material, washed it with a solvent, and just watched as the mixture beautifully separated into these distinct bands of different colors. Actually, the word chromatography literally translates to color writing. Pretty cool, right? From those really simple beginnings, the science just took off, evolving rapidly to gas chromatography in the mid-1900s, to today's highly advanced high-performance liquid chromatography systems, and now it's heading straight toward an AI-driven future.
But to really grasp how any of these advanced systems actually work, we've got to zoom way into the micro level. At its core, chromatography is essentially a microscopic molecular racetrack, and it relies on three basic components. The first is what we call the stationary phase. This is a completely immobile solid phase, or sometimes a layer of liquid adsorbed onto a solid support. Just think of it as the fixed terrain, like an obstacle course, completely full of hurdles that our molecule runners have to physically navigate.
Right, so the second absolutely crucial component here is the mobile phase. This is a flowing fluid. It can actually be either a liquid or a gas that percolates right through or over that stationary phase. So if the stationary phase is our track with all its hurdles, the mobile phase is this powerful wind at the runner's backs. It forcefully pushes the entire chemical mixture straight through the system. So bringing it all together, we have our three core components: the stationary phase, the mobile phase, and the separated molecules themselves. The real fundamental principle driving this whole separation is that molecules travel based on their relative affinities. Basically, some molecules are highly attracted to the stationary phase. They really like to interact with the track, so they get slowed down. Other molecules, well, they have a lot less affinity for the track and are just easily swept along by the mobile phase, so they end up winning the race. And because literally no two components have the exact same affinity, the runners naturally separate over time. And you see this principle perfectly demonstrated in one of the most common and vital techniques we use today: high-performance liquid chromatography, or HPLC for short. In modern HPLC, that stationary phase is packed into a column using extremely fine particles, usually just between 2 and 5 micrometers. Because these particles are so incredibly tiny, we're talking a fraction of the width of a single human hair here, liquid isn't just going to flow through them naturally. No way. We have to use incredibly high-pressure pumps to literally force the liquid mobile phase through the column. And that intense pressure is exactly what gives us the high performance, letting us analyze really complex liquid samples like delicate medicines with just incredible precision. Now, what's really interesting here is looking at what's actually happening inside that high-pressure column. Let's think about polar and nonpolar molecules interacting with the stationary phase. Say the stationary phase is polar. A polar compound is going to have a much stronger interaction with that polar stationary phase. It acts like a giant hurdle that slows it way down. On the flip side, a nonpolar molecule is going to have a much weaker interaction, so it just rushes ahead with the mobile phase. Eventually, a detector converts this physical separation into an electrical signal, giving us a chromatogram where every single separated molecule registers as a distinct peak. And that distinct peak is tied to an incredibly important metric we call retention time. Simply put, this is the exact finish time for each runner in our chemical race. It's the specific amount of time a compound takes to make its way through the entire chromatographic system. Because every chemical has a totally unique set of properties, its retention time under specific conditions acts exactly like a fingerprint. That's what allows us to identify mystery molecules with extreme sensitivity. Now, depending on the exact mixture we're trying to separate, each PLC is generally divided into two main classifications based on relative polarities. First, we have normal phase chromatography. Here, the stationary phase is highly polar. Think something like silica gel. And the mobile phase is nonpolar, like hexane. This means the least polar components elute or finish the race first. But then we have reversed phase, which, true to its name, flips this entire dynamic. The stationary phase is nonpolar, and the mobile phase is polar, meaning the most polar compounds are the ones that elude first. And looking at the atomic level brilliantly illustrates exactly how this reversal works. On one hand, normal polarity silica possesses these polar sites that readily interact with polar molecules, essentially grabbing onto them to slow them down. But if we take those exact same polar sites and cap them with non-polar groups like octyldecyl siloxane or C18, well, suddenly they interact strongly with non-polar molecules instead. We've completely changed the friction points on the track, which completely alters the elution order of our runners. Of course, while HPLC is absolutely perfect for handling delicate liquid-soluble substances, analytical chemistry is a huge field, and it requires a variety of specialized tracks for different types of molecular runners. For instance, gas chromatography, or GC, is basically tailor-made for light, volatile substances that easily turn into gas and are stable under heat. Think along the lines of perfumes or fuels. Then we've got size exclusion chromatography, which literally separates molecules purely based on their physical size. There's ion exchange, which separates them by electrical charge, and affinity chromatography, which relies on these highly specific lock and key type interactions. So, zooming back out to the macro level for a second, it's just truly awe-inspiring to consider how these microscopic races solve massive real-world problems every single day. I mean, chromatography isn't just some abstract lab exercise. It is quite literally how the pharmaceutical industry ensures the drugs you take are perfectly pure. It's absolutely essential in biomanufacturing for purifying complex, life-saving treatments like monoclonal antibodies. Environmental scientists rely on it to monitor hidden pollutants in our air and water, and it even ensures our food supply is safe by sniffing out harmful toxins and additives. And perhaps nowhere are the stakes quite as high as they are in forensic science. Techniques like gas chromatography coupled with mass spectrometry are absolutely crucial for analyzing crime scenes, conducting drug testing, and running toxicology reports. By separating and then undeniably identifying specific compounds in a sample of blood or trace evidence, chromatography provides the hard, physical truth that's needed to solve complex crimes, exonerate the innocent, and ultimately assist in the administration of justice. It's really powerful stuff. And the best part? The field is constantly evolving. Today, we're pushing the boundaries of what these systems can actually do. We are actively developing these incredible, compact, portable microfluidic devices that let scientists conduct highly sensitive on-site analyses, which drastically reduces sample consumption. Even the stationary phases themselves are getting major technological upgrades, with things like monolith columns and nanoparticle materials. We're even seeing a big shift toward using natural solvents to make these vital chemical analyses much more environmentally sustainable. Let's move forward and see how this builds directly into the future with the integration of artificial intelligence. Modern chromatography systems are already incredibly automated, but by bringing AI into the mix, we can actually mathematically predict retention times before the physical race even starts. And when we combine liquid chromatography with mass spectrometry, a technique known as LC-MS, AI can rapidly analyze these mind-bogglingly complex datasets, identifying compounds with a level of accuracy and speed that was, frankly, completely unimaginable just a few decades ago. We really have come a remarkably long way from just separating green pigments in a leaf, haven't we? We've essentially built this intricate, high-performance architecture capable of decoding the chemical makeup of our entire world. So as AI and microfluidics grow infinitely more precise, leaving practically no molecule unknown, what invisible secrets of the universe will chromatography reveal next? Thank you so much for joining me for this explainer. I really hope it provided a strong conceptual foundation for our upcoming advanced lectures. Keep questioning the physical world around you, and I will see you next time.